Hello, everyone. Thank you for joining us. My name is Walter Gonzalez. I am a senior electrical engineer and the group testing manager for ETAP's Electrical Safety Division. Today, we're going to explore ETAP's Arc Safety software suite, which includes electrical safety products used in a number of industries for generation, transmission, oil and gas, renewables, data centers, to name just a few. Electrical workers can be exposed to various hazards, so it's essential to not only identify but also quantify these risks to ensure their safety. With ETAP, you can assess electrical hazards such as shock, arc flash, lightning risk, underground cable magnetic field exposures. Identifying the relevant standards and guidelines for the analysis can be a challenging task. ETAP streamlines this process by ensuring compliance with various electrical safety guidelines and standards. For example, ETAP 2024 complies with NFPA 70E, CSA Z462 2024, the primary standards for electrical safety in the workplace used in the United States and Canada, respectively. Electrical safety practices and regulations vary globally. To ensure compliance, ETAP also supports electrical safety standards specific to Europe, South America, Africa, Asia, and Australia. This level of flexibility and compliance enables power engineers worldwide to adhere to local regulations effectively. Now that we understand ETAP's compliance with various electrical safety guidelines, let's explore how we can access these features. In ETAP 2024, we can utilize the new Power Ribbon menu to set up our arc flash studies. This modern interface enhances efficiency and streamlines the setup process. To view all of our tools, we select the arc flash group, which will transform the Power Ribbon into a centralized hub with useful tools for setting up an arc flash study. After configuring the arc flash study type and study cases, the Power Ribbon provides a clear summary of the calculation methodologies and standards applied. The Power Ribbon also streamlines data entry by offering convenient shortcuts to frequently used interfaces for global arc flash input data. You also have shortcuts to streamline the creation of predefined arc flash calculation scenarios to model different facility operating conditions without the need to move to another interface. Using the built-in troubleshooting tools such as the arc flash result analyzer, arc flash calculators, and time current curves, we can easily identify fault locations with high incident energy exposure estimates. This streamlines the process of determining incident energy mitigation recommendations for arc flash studies. Once you're satisfied with the evaluation, the ribbon bar also provides easy access for standard and custom arc flash warning labels. Now that you have a better understanding of how to use the new Power Ribbon, let's explore the unique tools ETAP has to offer. When performing an arc flash analysis, it's common to struggle with determining the input data. A single piece of equipment can present multiple variations, such as fault currents, gaps, enclosure dimensions, working distance, and electrode configurations. To account for these variations, multiple scenarios may be needed to quantify how much the arc flash results can differ. Additionally, by the time the arc flash analysis is conducted, the system protection has already been established. As a result, changing protected devices or adjusting settings on existing devices may not be feasible. To address these challenges, ETAP's patented constant energy area boundary curves can be used for AC and DC systems as of ETAP 2024. The C area curves represent a statistical analysis of arc flash input data variations, yielding a range of results bounded into a single area, where this area represents all combinations of parameters that will yield a desired incident energy exposure limit. The pass or fail criteria then becomes trivial, which is to verify the protected device trip curve is to the left and below the C area curve. When this is true, the desired incident energy design limit will not be exceeded while considering many input data variations. ETAP C area plots are true game changers as they allow protection engineers to consider arc flash during the protection and coordination phase of the system study. This helps improve efficiency and allows engineers to design for reasonable incident energy exposures. Let's take a look at some of the other tools ETAP provides to enhance your efficiency, starting with tools for conducting a comprehensive DC arc flash analysis. With the increasing use of renewable energy and battery energy storage systems, the question often arises, which DC arc flash methodology should I select? This can be a difficult question to answer given the abundance of options available. ETAP simplifies this process by complying with industry-accepted methodologies. ETAP also provides its own industry-leading adaptations of these methods, which have been validated against recorded DC arc flash events. This includes methods for photovoltaics that apply rigorous DC arc flash methodologies, while also considering the equipment's IV characteristic curves. ETAP 2024 introduces a new transient DC arc flash algorithm specifically designed for battery energy storage systems. This method factors in battery rising and decay time constants, along with dynamic conductor effects like erosion and elongation. These methodologies empower engineers to improve accuracy and reduce over-conservatism for DC arc flash analysis. ETAP also includes features that allow power engineers to perform an arc flash analysis for various types of AC systems. For example, in oil and gas applications, when evaluating low-voltage equipment, a common challenge is efficiently accounting for varying arc flash input data due to differences in equipment characteristics and typical work practices. ETAP's solution to this is the enclosure editor, which empowers engineers to perform a compartmentalized arc flash analysis. The enclosure editor can also be used to model common scenarios, such as multiple electrode configurations, within a single enclosure, to determine the worst-case arc flash results with minimal effort. Another challenge commonly faced is the analysis of fault locations near generators, which required a detailed analysis to consider the significant fault current decay present. ETAP addresses this by supporting the option to model generator decrement curves and motor fault current decay over time to improve accuracy in the arc flash analysis. Next, let's focus on the evaluation of systems with renewables, such as photovoltaics or wind turbines. These systems include equipment rated above 15 kV, where the challenge is finding a method that is appropriate for this voltage class and avoids being overly conservative. ETAP's arc fault methodology addresses this with support for line-to-ground, line-to-line, and three-phase arcing fault analysis, using empirically derived methods based on high-voltage arc flash tests. ETAP's arc fault method is highly versatile, capable of analyzing three-phase arcing faults on 34.5 kV collectors in wind farms, as well as line-to-ground arcing faults along high-voltage transmission lines. Arc fault also includes comprehensive built-in typical data, consideration for transient overvoltage, and altitude correction factors based on guidelines from the IEEE's NESC C2 standard. My colleague Raghu Veeraraghavan, a senior electrical engineer and department manager of ETAP's Electrical Safety Division, will now provide a demonstration of ETAP's ARC safety tools.
Hi everyone. Thank you so much for joining the arc flash safety demonstration with ETAP. I'm your host, Raghu Veeraraghavan, and I'm excited to be here to present the features that is discussed in the presentation in the beginning and to show a quick demonstration on what are the capabilities of ETAP software that will give you a good spark. ETAP offers a user-friendly and analytical experience on identifying the right arc flash method for the right application. The arc flash group offers a one-stop shop in combining the AC and the DC modes using the ribbon bar interface. This gives an upper hand on selecting the correct study based on the compliance and the requirements specific to the standards across the globe. For example, voltages ranging from 0.208 kV to 15 kV, the selection of IEEE 1584 method is applicable. And the calculations ran using the IEEE 1584 method can easily be selected using the AC arc flash mode. Shifting voltages above 15 kV that may involve distributed energy resources, connecting the grid for stability, the arc flash method is also useful for performing the arc flash studies beyond 15 kilovolts in such conditions. By using the ribbon bar, ETAP ensures to give the right methods for the right applications. Basically, you miss it in case we fix it for you. With the power of the digital twin technology, ETAP can run several scenarios concurrently with its three-dimensional database. However, this list can grow significantly. ETAP ribbon bar allows to filter the scenarios according to the compliance and application to organize them visually. As you can see, if I'm in the actual 1584 study methods, the corresponding study cases and the corresponding scenarios are available in the drop-down. For example, if I switch to the DC arc flash analysis, only the DC arc flash methodology related study cases and their respective scenarios are available. The next ETAP ribbon bar feature that offers intuitive and easy to understand display settings without the opening its interface every time to change units. As an example, if I run an arc flash study beyond 15 kV where we have distributed energy resources like wind turbine generators or inverters, which definitely provide a proper voltage write-through capability based on the IEEE 1547 standard that requires to have a proper stability to the grid. They all basically rely on the bus terminal voltage. With the ribbon bar, it is very easy to toggle between the units to display the actual percentage of the voltage based on the percent of the nominal kV or based on the actual voltage drop across the terminal bus using the toggle feature button. On top of that, you have the ability to show the different sequence currents, the phase currents, and the 3I0 values while running the line to ground fault. And this can be achieved without actually opening the display option editor and have the ability to show the different distribution of the currents within the one-line diagram in a quick fashion. ETAP ribbon offers command shortcuts to identify arc flash related study tools without even searching for them visually. For example, frequently used tools like fault insertion can be typed into the command section, and that would automatically trigger the fault insertion toolbar, and that would determine the overall sequence and the selectivity of the power system. Another useful feature is ETAP ribbon can be customized to have keyboard shortcuts that is used frequently and help reducing clicks, and use it according to the customer's convenience. For example, if I want to launch an arc flash calculator with a keyboard shortcut in my ribbon bar, I could be able to perform using the right-click menu to customize the ribbon and click on the keyboard customize. I have the ability to select my IEEE 1584 arc flash calculator with a key called C. And once it's assigned, if the customer clicks on C on the keyboard, it launches the arc flash calculator immediately without being searching for the calculator in the actual toolbar. Another application of interest is protection and coordination. We all provide proper coordination settings and relay settings for protective devices, protecting equipment and the branch currents, transformers, motors, etc. However, this protection and coordination settings are done based on actual bolted fault currents. When it comes to arc flash, especially low voltage, the nature of arc and its resistance can have a significant reduction in the arcing current, which could be as low as 50% of the bolted fault current. So in this case, the whole protection and coordination settings needs to be revised based on the arc flash settings. Let us consider a particular location of this bus C Let us consider this location. If we happen to know the maximum and the minimum bolted fault current on this location based on all the scenarios that we ran for short circuit, and we provide a constant energy area of 8 calories as a function of current and time, and provide different equipment variability considerations such as gap, height, width, and depth, and the working distance, along with the variation in the electrode configuration, the program determines a graphical representation of incident energy as a function of current and time. If the incident energy reference value is available in the time current, it is easy to select the corresponding protective device that is always left and below of this particular constant reference boundary area. And after that, regardless of the calculations and the input parameter variations, the program will give you the incident energy still less than the actual C area or the constant energy area. By doing this, you save a lot of time and at the same time do not compromise the protection and the coordination settings for the bolted fault current as well as the arcing currents. The same technique can still be applied to the DC arc flash application. Consider for this inverter combiner box, if we are able to get the maximum and the minimum fault current on this location and apply this constraints for the constant energy of 4 calories with the given variations in the equipment and the corresponding configuration, the C area plots are available in the time current curve. As you can see, with the current settings of the fuse, the C area plot is already been overlapped by the fuse settings. And by coordinating within the C area plots, adjusting the fuse settings will give us the correct desired incident energy less than 4 calories per centimeter square. Another application of ETAP DC arc flash mode with the evolving renewable technology using battery energy storage system and the increase of lithium-ion batteries, the DC arc flash at the battery terminals could be very challenging results when we do software simulations. For example, in this case, using the available regular DC arc flash methods, calculating the DC arc flash at the battery terminal or the fuse disconnect could be overwhelming with a very high magnitude of the arc current and the incident energy accumulated over the time. With the evolution of the transient method, we have the ability to basically get the calculation using the IEC 61660 to tap the actual battery time constants and the corresponding internal resistance of the battery, taking it as a reference, and evaluate the incident energy based on a function of time that is solely dependent on the dynamics of the short circuit current provided by the battery. Using the duration and the time step of the current, a nice profile of the arcing current and the accumulation of the incident energy over the time can be captured in the ETAP software. As you can see, the realistic calculation of the incident energy at the time which the fuse has limited the current, or maybe the fuse that has operated very fast, can be easily calculated using the arc flash transient method. So previously the value was around 162 calories per centimeter square, but with the correct estimation of the current being calculated and the rise in the time constants provided by the battery, DC capacitors, DC motors can easily be tapped in the calculation. So this would clearly explain the overall rise in time of the short circuit current and the corresponding accumulation of the incident energy. The greatest thing here is the program can be able to give you a graphical plot that captures the bolted fault current, arc voltage, arc energy, and the incident energy based on the actual characteristics of the battery storage system, and also can give you a reference point where the fuse would operate. On top of that, the program also accounts for the elongation effect and the erosion effect, where in this case for a high magnitude of current like this value, the copper conductors would automatically get eroded, giving us a large gap, and the capture of the incident energy until the copper conductors gets eroded can still be captured in the program. As you can see, the combined effect of the arc erosion and elongation would give us a good profile of the incident energy based on the actual physics of the arc and the way the conductors gets eroded for a high magnitude of current. So it could also provide us an accurate simulation on how to calculate the incident energy for these sophisticated locations without compromising the conservatism given in the incident energy values. Overall, running arc flash from starting from renewables like PV arrays and energy storage system, capturing the actual irradiance of the PV arrays, or capturing the actual time constants of the battery, and then moving on to the inverter side on a 480 volts or 600 volts, and then get the incident energy using the 1584 calculations, and then overall calculating the incident energy on any applications like refineries or oil and gas, and then moving on to the high voltage application where we ensure grid stability using the arc flash method, using the EPRI equations or any arc fault method that is applicable. On the whole, the program also offers several reporting and deliverable tools to make arc flash labels using the custom label option or the e-label option. It could be very useful to generate arc flash labels based on the corresponding standards or the international locations that is supported by the arc flash analyzer. So in this case, you can be able to choose either based on NFPA 70E or NESC, or based on the arc energy using the German standard as well. Finally, I would like to conclude by saying that sometimes all it takes is a single spark to cause an arc flash. However, ETAP is the spark that transforms complex arc flash analysis to identify and mitigate hazards using accurate simulations for a safety workplace. Thank you very much.
Thank you for the insightful demonstration of ETAP's Arc Safety Suite, Raghu. As we saw in his presentation, ETAP's Arc Safety Suite aids in analyzing electrical hazards, including shock, arc flash, lightning risk, and underground cable magnetic field exposures through its specialized products. This is done through compliance with various electrical safety guidelines and standards used across the globe. ETAP prides itself on dedication to compliance. It is also an industry leader, developing unique solutions which aid common industry challenges. Innovative products like ETAP's patented C-area plots have become game changers by allowing engineers to be proactive and design for a reasonable incident energy exposure during the protection and coordination phase. ETAP's unique proprietary calculation algorithms aid in the analysis of AC and DC equipment that is present in generation, transmission, oil and gas, renewables, and data center applications. With ETAP's Arc Safety Suite, we can rely on electrical safety products which are intuitive, efficient, and accurate. That brings us to the end of the session. Thank you all for attending.